Hi there, welcome to Unit 1, Lesson 11. Today's question is, what is the same? Meaning, what are we describing by this term, the same? What does that actually mean when it comes to 8th grade math? We're going to decide that, and we're going to gain a better understanding by the end of this lesson what we mean when we say that shapes are the same. The first thing we want to do is we're going to compare some shapes to see what kind of shapes are the same. Before we continue on, I need you to go ahead and go grab 4 colored pencils. If you want to grab an entire pack of colored pencils, that's fine, but you need at least 4 for today's lesson. All right, welcome back to the video. Go ahead and select one of your colored pencils, one color, and what we're going to do is a person's right hand, or a person's hands are mirrors of each other. So like what we see, like, wow, my hands are really big. So we'll just go off of this. When we see a left hand next to a right hand, we see that thumbs are next to each other, and we see that fingers are all opposite of each other, and we can say that they are on the opposites of each other, or mirror images of each other. In this case, the left hand is labeled, and what we're supposed to do here is shade all of the right hands. So let's go ahead and do that. If this is the left, then the opposite of this must be the right. So we're going to go ahead and shade this one. As I look around here, this one appears to just be rotated slightly around this one. This one appears to also be a left hand that's kind of slightly rotated. This one appears to be a right hand as well that's been slightly rotated in comparison to this one. These others are a little tougher to see, so I'm going to go ahead and rotate my whole paper to see them a little clearer. Now that one's clear to me. It's a left hand. This one is a right hand. These two appear to be almost a reflection of each other across here, so I'm expecting this is a left hand, but I'm going to double check just to see, and I see that it is a left hand for sure. When we look at that, how many left hands are there? Well, I see that there's 4, and I also see that there are 3 right hands. On the next page, we talk about this question now, are they the same? As we get into this, what we want to look at is we're going to use the principles that we've been using for the last couple weeks, talking about rigid transformation, to help us to identify when 2 figures really are the same or not. When I look at these 2 figures, first off, I can look at them and say, you know, those look an awful lot like they're the same, but I want to be able to make sure that they're the same. And so what I'm going to do with this is I'm going to go ahead and take a piece of my tracing paper or patty paper. And I'm going to go ahead and I'm going to set that on there. And then to verify if these 2 figures are really the same or not, I'm going to go ahead and bring this over here. So I'm going to translate this figure to the right, and then I'm going to rotate what looks like 180 degrees. And I see that those 2 figures actually are the exact same. They map right onto each other. So I can go ahead and confidently say now that these 2 are the same figure. When I look at figure B and I see this rhombus compared to the other rhombus, the thing that really stands out to me is the height. Also, this angle right here is a much sharper angle than it is over here. I see a couple things that are obviously different. There is no rigid transformation that would take this rhombus onto this rhombus or the other way around. We could say that these ones right here are not the same. Letter C. Wow, at first glance on that one, I see almost looks like a couple eyeballs looking at me. I see what appears to be a reflection line that's right in the middle. We can go ahead, of course, and take our tracing paper just to double check to see, are these for real? Like, are these definitely the same or not? Just a rough rough sketch of it to see if they're there. I'm going to use the reflection, and I'm going to see that, you know, those figures, based on my crude drawing of it, they are the same figure. There's just a reflection of one figure to the other. So I can go ahead and I can say these ones are the same. As I look at figure D, these polygons here, again, I see kind of the same relationship that I saw up here in figure D, or figure B. The first figure of D is much taller than the bottom figure. I see a couple other little instances, like this height is different, this height is different. So the corresponding lengths of the segments are not the same. Up here we saw that the corresponding angles are not equal in measure. These ones, corresponding angles are all equal, but the corresponding lengths are not. So we're going to say this one is not the same. As I get to figure E, I see two puzzle pieces. I see a 90-degree angle followed by a little impression here at the top. I see the same thing here. I come around to the side with this little piece that's sticking off, and I look at this side. I see a piece sticking. Oh, wait a minute. Something doesn't feel right about that piece. It really looks like this little piece sticking off the edge is actually much lower than this other side. I'm going to go ahead and use my tracing paper here. I'm going to draw right next to that first figure we did just to verify. I'm fairly certain these two figures are not the same, but when I go ahead and compare using a transformation sorts where I'm going to translate this figure over here and rotate slightly, that little segment, that little nub sticking off the side, that's not in the same position. Because of that, this is now disqualified from being the same. We would call this not the same. So then we're still left with that question, looking at these pieces and saying, what do we mean by same and what do we mean by not the same? Well, to get a better understanding of that, we use the principles of area and perimeter to help to describe whether something is going to be congruent or not. So we see this new word right here, congruence. This is the big word of this lesson, or the big vocabulary that we need to get from this, that we need to transition from the word same. In this case, what we've commonly been calling it is saying same, is now we're going to be calling things congruent. So how do I know if something is congruent? Perhaps at this point you've heard of the phrase same size, same shape. But what does that actually mean? When we talk from a mathematical standpoint, we talk about the size of a figure being based on the length of the segments and the angle measures that it makes up. We can use those two principles of segment length and the angle measures to help us with area and perimeter, as well as with just establishing congruence. When we look at these questions here, so here's our figures. Question 1, which of these rectangles have the same area as rectangle R, but different perimeter? We look at number 2, which rectangles have the same perimeter, different area, and then same area and same perimeter. With those things in mind, let's go ahead and go to each of these figures and let's determine area and perimeter of each of these rectangles. Just for a quick review, when we talk about the area of a rectangle, we are talking about finding the area as being the length times the width. And when we talk about perimeter of any rectangle, I'm going to abbreviate that, we're talking about the perimeter is equal to twice the length plus twice the width. So as we see that, we're going to go ahead and use this around here. I can already see some similarities, some things that I'm kind of going to make some predictions on and see if I'm right. But I think that it looks like angles or rectangles A, R, and E appear to be the same. B and C, they appear to be the same, and D and F appear to be the same. But we're going to use some things to double check this and make sure. First off, figure R, let's find the area by taking the area of the length times the width, 2 times 3, and we find that the area equals 6. When we find the perimeter, we find that the perimeter is equal to twice the value of the length plus twice the value of the width, or 4 plus 6, so our perimeter equals 10. I'm going to go ahead and put that right inside here. Let me verify that. Perimeter here is 10, and then area is equal to 6. If this is not making sense to you, an area, what you'd like to look at is adding up all 4 sides, and we can certainly do that. 2 plus 3 is 5, and 2 plus 3 is 5, so 5 plus 5 is 10. I made the prediction earlier that I believe that this triangle or this rectangle is the same as this rectangle right here, just for the purposes of where we're at. This is figure R. I learned earlier that if I do a sequence of rigid motions, I can verify if my shapes have the same size and the same shape, or that I can actually begin to verify congruence. If I take figure R and I translate it down here and do a rotation, these are of course crude things, I see that that rectangle is exactly the same as that one. And then I see if I do the same thing over here, I see that figure R maps directly to figure E. With that rigid transformation, I can see that figure A will have an area of 6. Just a quick verification, 3 times 2 is 6. And a quick verification of the perimeter, 2 plus 3 is 5, plus 3 more is 8, plus 2 more is 10. And I can verify that that's true for both of these. As I look at figure C, I see figure C, my area is equal to 6 times 1 for an area of 6, and my perimeter is equal to 2 times 6 plus 2 times 1. So we have 12 plus 2, my perimeter is 14. I look at figure B, which I gave the prediction that B is the same as C with dimensions of 6 by 1. This tells me that the perimeter is also equal to 14 because of over here, 6 plus 6 is 12, plus 1 plus 1 is 14. And then my area of 6 times 1 is 6. Finally, I'm left with D and F, and these ones look the same. I see the same measurements. So what we'll see with this one is their area is 4 times 1 for an area of 4. And then for a perimeter, that almost looks like a 7, but it is a 1. Perimeter, we have 4 times 2, which is 8, plus 2 more is 10, so perimeter of 10. And then over here again, same thing, perimeter of 10, area of 4. Now that I have a little bit better classification system set up, I know which rectangles are exactly the same. I can make my better comparisons. As I go through these, I see the question, which of these rectangles have the same area as rectangle R, but different perimeters? So when we talk about area, let's look at these. We see an area of 6, area of 6, 6, 6, 4, and 4. These ones have different areas, but these ones all have the same area. So which ones have the same area as rectangle R, but different perimeters? The area of here is 6, but the perimeter is 14, so that makes figures B and C the same area, but different perimeters. When we talk about problem 2, the same perimeter, but different area. Okay, well, let's look at perimeters. I see 10, 10, 10, and 10, 10, 14, and 14. When we look at these, it looks like I have 2 different groups. Rectangles with the same perimeter, but different area. I see the grouping of A, R, and E have the same perimeter as F and D. So those ones all have the same perimeter, but they all have a different area when we consider them in groups. Third question asks us, which have the same area and the same perimeter? Well, I think we already established that. There's 3 different groups I could look at here. There's the group that has A, R, and E. There's the group that has B and C. And then there's the group that has D and F. What we've just done is classify these rectangles into groupings of like figures. Your 4 colored pencils are for this purpose right now. Choose 3 of them. And we're going to go ahead and we're going to color in the rectangles that actually show congruence. So when we talk about this, we ask the question was, what does it mean to really be congruent? When we talk about congruence, we're talking about the overall shape and size of the figure, but shape and size come down to several factors. The most important factors when we're talking about congruent is we're talking about the corresponding segments have equal length. And then the other big key factor is corresponding angles have equal measure. This should sound very familiar to everything that we've been doing with rigid transformation, recognizing that under a rigid transformation, every element of that shape, all the lengths of the segments, all of the angle measures, everything about its size and its shape remain exactly the same. So when we talk about congruent, it's no longer sufficient just to say the same size and same shape, but to understand that the same size and the same shape really means that we have all of the segments are of equal length, the corresponding segments are of equal length, and the corresponding angles have equal measure. So as we go through this, what we look for in this is we see that starting with figure R, we see that one has an area of 6 units and a perimeter of 10 units, as does figure A and figure E. These three yellow figures now, figures A, R, and E, are said to be congruent because all of their segment lengths, their corresponding segment lengths are equal and their angle measures are equal. We can understand that the area and the perimeter help us out with that to determine that these figures are the same measures. Figure C and figure B also have equal areas and equal perimeters. And then finally, figure D and figure F have they're congruent rectangles. With this information, we're ready to look and understand about how area and perimeter play into this. And we're actually going to do that through a little bit of a challenge question. It comes in this shape. So we have in square ABCD, points E, F, G, and H are all midpoints of their respective size. Remember that midpoint means that they are in the middle of their segment. Our thought is this, is what fraction of the square is shaded? So this part is shaded. What fraction of the entire area here is shaded? We need to explain our reasoning. Go ahead and make a prediction on there. Do you think that it's like a third or a fourth or a fifth or a sixth? Maybe it's half. What do you think it is? Go ahead and put that prediction down on your paper. And now let's do a couple things with this. Let's actually make some predictions with this. If these are midpoints, then if I connected these right here, this would make squares. And I could see that I'm looking at a fourth of the figure. Now, if I go ahead and I take some tracing paper and I look at that figure, I'm going to go ahead and take the figure right here of the shaded region, and I'm going to go ahead and compare it to those regions that I made into fourths. And what I see right away is here's that line that separated out the fourth, is I can see that that shaded region doesn't quite fill it in all the way. So whatever my prediction was at the beginning, if I predicted 1/4, I now see that I was wrong. I need a little bit more. So how can I verify that? You know, we just talked about this thing with area, and we just talked about how the area of the figure is based on the length and the width. Let's see if we can use that along with rigid motion to understand this problem a little better, to know what fraction of the square is shaded. Well, let's take, with our rigid motion, let's take this piece right here, this bigger piece right here, and let's go ahead and use a rigid motion with this one. I'm going to use rotation to rotate this piece, kind of like picking it up out of the puzzle and rotating it onto here. I know that this length right here must be equal to this length because point E is a midpoint. So I'm going to go ahead and take this part of the figure, and let's pretend like I'm cutting it out. And I'm actually going to go ahead and rotate around here, around point E, 180 degrees until it maps here, and I see that I now have a square that's in the same position. Let's see what that square looks like. When I go ahead, I'm going to draw it out right here. Okay, that square is here. And then I want to compare that square to my original square. And I see that that square is actually the exact same size as my shaded region. By doing this, I can tell myself a couple of things. If I've combined these two pieces, these two sections, by combining these two sections, I've created one whole unit. If all these other figures are the same, like if this piece right here is the same, that's interesting. Knowing this is a square, knowing these are lines, then each of these pieces all being the exact same, I can perform that same operation right here and right here, that rotation of 180 degrees, whoops, right here, as well as right here. And what I actually end up with is I recognize that there are 5 equal size squares to this shaded one in the interior region. Those 5 squares come from combining those 2 red sections together, combining those 2 yellow sections, these 2 aqua sections, and finally these 2 blue sections. With this understanding, I should know now that 1 out of those 5 sections is shaded. And it's up to me to explain my reasoning now. Well, my reasoning is that by basic rigid motion, moving one of these figures, you could take this triangle to here and you'll see the same result. But using basic rigid transformation, I see that the combination of these 2 equals a square that's equal to the size of this inner shaded square. And I can recognize that through translation. So by explaining my reasoning, rigid transformation, a rotation around point E of this section, creates a square the same size or an equal size to the shaded region in the middle. And then I see that that same rotation at these other various points around each midpoint demonstrates that I have 5 equal size sections and only 1 out of the 5 are actually shaded. Quite a bit. So with that, let's talk about this concept of congruence. We've seen congruence all the way through. Congruence might be a relatively new term for you, for an idea that's been being used for a long time that you may just be compared to as saying the same, the same, the same. But now what we should know about this is that same is not sufficient. When we say that 2 figures are congruent, if one can be lined up exactly with the other by a sequence of rigid transformations. So rigid transformations actually proves congruence. And the reason it proves congruence is because of the fact of these 2 things, that corresponding segments are equal in length and corresponding angles are equal in measure. And when we have corresponding segments equal in length, corresponding angles equal in measure, we have a rigid transformation, which means that we have 2 shapes that are exactly the same figure. So an example that we might look at is this. Triangle EFD is congruent to triangle ABC because of the sequence of transformations that happened here. We recognize first off that triangle ABC, there's a lot on this one. Let me get rid of a few things. Hopefully it's less confusing. Sorry about this. All right, there's the original triangle, triangle ABC. We see that a reflection across segment AC followed by a translation from B prime to F maps the original triangle ABC onto the image of triangle ABC, which is going to be known as triangle EDF. Those rigid motions, if you notice that all corresponding angles and corresponding sides are equal in their measures. When we talk about congruent, we need to recognize that that means that all corresponding angles and all corresponding lengths are equal in measure, making the exact same shape after every rigid transformation. A couple of key things to remember with this. We don't have to check the measurements to prove that 2 figures are congruent. All we need to do is just have enough of them in a sequence of rigid motions to match the figures up, and that can prove congruence because of the laws of rigid transformation, where I know that the lengths of the segments of the corresponding sides are equal in measure. We also know that a figure that looks like a mirror image of another figure can be congruent to it. This means that there must be a reflection in the sequence of transformations when it matches up the figure. We saw that when we looked at this figure right here. We see that these figures, that this is not a reflection, so this one we don't see the same property that we did before, but we definitely see that here, that this reflection proved that these two figures were congruent. A rotation of 180 degrees proved that these two figures were congruent. Finally, since two congruent polygons have the same area and the same perimeter, another way to show that two polygons are not congruent is to show that they have different perimeters or different areas. A lot of things to take in today. The main concept is that all the work that we've done with rigid transformation, recognizing that the shape does not change its corresponding length of segments, or it does not change its corresponding angles or corresponding side lengths, that they have to be equal. This is what proves congruence, and this is what we mean by congruence. Thanks for sticking in today. Thanks for working hard. I really appreciate what you do. I know that we can do hard things, and I know that you're doing great work. I really appreciate all that you're doing. Please make sure to email me with questions and check in when you're not sure about how to do stuff. And remember, never, ever give up. You're doing great.